Right.
You did a good job with that.
Good morning all, welcome to the mechanical engineering section of this workshop. I'd like to introduce Dr. Holmes. David is a mechanical engineering lecturer here at JCU, but I'll let him tell you more about himself. Yeah, so thanks, Dave.
Yeah, no worries. Thank you. Thanks for coming, everyone. So I'm going to talk about a few different things today. The main thing is that I'm trying to illustrate a couple of practical examples of where some maths and physics theory actually gets applied in practice.
Any chemists left here?
No, I've lost one already.
So the first part of this session I'll talk about some simulation techniques that I do as an engineer, so writing simulation codes to analyse different things as engineers. Perfect, thanks Robert. And then in the second part we'll do a little bit of some of the forces, trigonometry, things like that, related to calculating the centre of gravity of a vehicle. And that's an application that we're going to do over here, but we can actually apply that to a lot of different classroom experiments as well, and I'll talk a little bit about that. Something a lot simpler than putting a car on a force transducer and working out where its centre of gravity is. So before I get into any of that, I guess this is a slide that Robin might have even had in his previous presentation. I'm not sure if he did. It's one that we show to a lot of school kids and say, engineering is the combination of science and maths and all this kind of stuff. A lot of the time it doesn't actually mean a lot to them. They do science and maths and they don't actually understand how that comes together in engineering. And the purpose of this first part of the presentation is to try and illustrate that at least in one application. So before I get into that, just what have I done, where have I come from? I did my high school here at Cathedral in Townsville. Before that I went to Cranbrook Primary. I did my degree here at JCU, so I'm very familiar with the program, particularly the mechanical program. I did my PhD here in engineering, and that's when I started doing the computer modelling side of what mechanical engineering is. After that, I was lucky enough to get a postdoctoral fellowship at MIT for almost 3 years over in Boston, and that was an amazing experience and really enjoyed it. And it was sort of indicative of what a lot of the engineering graduates do, which is to travel in different places. I did it as a research engineer, so with a PhD, but a lot of our graduates, all over Southeast Asia and various other places as pipeline engineers, design engineers, and various other things. So one of the major advantages when we're trying to sell engineering to the students who might choose to go there is the ability to travel. It's really the qualifications that you get, you don't need to re-qualify in a lot of different countries, so you can just practice as an engineer all over the world. And then in 2010 I came back to JCU and I've been a senior lecturer since then, teaching mechanical design and programming and various other things. So, modelling in mechanical engineering, and this is what I really enjoy doing, has lots of different applications, but basically we deal with a lot of components that are much more complicated than what you can actually analyse by hand. And so whenever you have a geometry or a load case or some sort of situation where it's much more complicated than what you can actually analyse with a pen and paper, we use modelling. And what modelling does is tell us where the critical zones are. So for an example, with solids, if we've got cars crashing into walls and gears and all sorts of things, these red zones are where the most force density is, so stress. I'm not sure if you know about the concept of stress, but basically it's just how densely is the force populated in the material. The more force that you get through a single bit of material, the more likely it is to break, and we have all sorts of failure criteria that tells us when it will or won't break. So that's what we're using here. Now particles, which is something that I'll talk particularly about in this presentation, is very useful when you've got things like hoppers and conveyors and anything you might see out the port to actually design those different configurations such that you're not damaging material, you're not getting material held up in places. If you've got food, then definitely you want first in, first out. You don't want certain food, grain and things like that getting stuck and waiting months and months to actually get moved out of a hopper and that kind of stuff. So the design of that equipment, excavators and so forth, we can use those particle simulation techniques. And then another area of mechanical engineering which is quite big is fluid flow analysis. And one thing I'll talk about as I go along, what I was doing over in the States was fluid flow stuff. So all of these are different simulation techniques that engineers use on a day-to-day basis, particularly mechanical engineers. And the maths behind them on a very fundamental level is very similar across all types of simulation, and that's what I'll be talking about. So here's just some examples of what we get the students to do in class around particles. So by about third year, they can do it in second year. It's pretty simple programming, but this is what they actually do as their introduction to this numerical simulation. I get them to code up one of these particle codes. And what the particle code does, this is a program that the students would write. Basically, you just have balls and gravity, and they bounce around and do their thing. So actually programming where a ball is in space and when it sees another ball and what force it gets from that and how the interaction, thinking about pool balls bouncing off one another and everything like that is what we actually get them to code up. Now this is a little experiment that I get them to do. They've got a hopper up the top and they've got to create some sort of wall geometry to get all the balls in this part as quick as possible, just to make it a bit fun. And this is one example of that. Basically, you just guide all the balls in. So this is a very rudimentary 2D version of something more complicated like what I was talking about a minute ago, which is like hoppers and conveyors and that kind of bulk material handling type systems. But the idea of getting the students to actually program this and understand the maths behind it is that this maths then reflects on all of the other type of numerical methods they might use. And I'll show you that in a second. Here's some practical applications of that. Is a conveyor going through a hopper system down onto another conveyor, and you want to minimise the amount of damage that the material gets, and you want to make sure that it doesn't get stuck up anywhere or anything like that. So this is an industrial application of that type of problem. You can see that there's probably in the order of almost 1 million particles there, so you've got computer tracking them, working out which ones are hitting walls and which ones are hitting each other and all that kind of stuff.
So why are they different colours?
Different colours is for, I believe, the different velocities in this simulation. So blue is, it might actually, let me start that again and I'll just check it. What is it? It's height, I think. Yeah, so you can have different contour plots for any of the different types of variables that you have. This particular one, I think, is just blue at the top down to, let me have a look. No, I think that is velocity. The faster it goes, the redder it is. Yeah. So you can simulate velocity, you can simulate material damage with a contour plot, all of that kind of stuff. So the colours in any of these plots are just telling us a parameter. And I don't have the actual key on this video, so I can't tell you exactly, but I'm pretty sure it's velocity by the looks of it. And then here we got, and this one's definitely velocity. We've got an excavator bucket. You can see the faster they move, the redder they are. And obviously that's not very good excavation, but you can see the proof of concept, why you might actually do this. With excavator buckets, one of the biggest things with those is the amount of energy you need to cut through the materials for a particular excavator bucket geometry and how much wear you get on those excavator buckets. Because if you can make a many $1,000 excavator bucket last twice as long, then you're saving a heck of a lot of work and money, particularly in the mining industry. Anyway, so this is the crux of it, where all of that calculation comes from, where the maths comes from and what we're actually talking about today. So it's a combination of vectors and differentiation and integration and then Newton's law of motion. So all of those things are things that certainly the year 11 and 12s I believe would be familiar with, and this is where you start to bring those together. So the first thing over there on the left, we've got particles, and for any of those codes that we were just looking at, what we're interested in is where are those particles and what is their velocity and potentially how much force is being exerted on them. Those types of information is what we want to track over time. Alright, so it's no good just knowing at one point in space, you want to know over time how that's going, because as that excavator bucket digs through, obviously everything's different at every small time step in time. And what we have is we can illustrate these with a number of different vectors. All right, so we have the velocity of a particle is a vector. The position of that particle in space is a vector. All right, you might have some origin in space. And then the force on each of those particles is a vector as well. All right, and we might have the example that the students were doing, that's a 2D example, but for the most part you have this in 3D for a proper code. And we have to work out how these vectors change over time. And we can't have a continuum of time because obviously, you can't in a computer calculate something in a continuum sense. So what we do is break time up into small little steps. All right? And so at the current step, we calculate what everything is. Then we say, all right, in maybe 0.1 of a second or 0.01 of a second, what's everything again? And we illustrate it much like the way that a video works in frames. All right? And so that's what we need to be able to do. Now, what we use to do that, we have differentiation and integration of rules relating acceleration, velocity and displacement. So you guys will have seen all of those ones at the top there. Obviously, acceleration is the differential of velocity with respect to time, and velocity is position with respect to time. And so if we know acceleration and we know the time step, we can get back to position, which is the fundamental thing that we want to calculate for these particles. So the particles, if we know where their position is, we can, from that have velocity and everything else. All right. So if we discretize this in terms of time steps, so rather than a continuous acceleration over changing acceleration over time, we just say time step n plus 1 equals the velocity at that time minus the previous velocity divided by the change in time between. And then if we have that equation, we can actually integrate that by just rearranging it in the very simplest sense. So that goes over there, we take that over there, and we have the velocity at the next time step equals the current velocity plus the change in time times the acceleration. All right, so if we know the acceleration of a particle, we can work out what the new velocity is. And the same thing with the velocity equation relating that to the position. We integrate that, and we have the new position equals the old position plus dt times the velocity in the new position. All right. And so if we start at time 0 and we know the velocity and we know the position at time 0 and we know the acceleration, then we can work out what the position and velocity and everything is at the next time step, and we step on like that throughout the program. So the program just has a loop and it just calculates steps through time like that. All right, so what that means is all we need to do is calculate the acceleration and then everything else comes together. Yeah? So here it is. Pretty easy. Newton's law of motion, force equals mass times acceleration. And if we know the forces, we can get the acceleration by rearranging that. All right? And so now, instead of having this velocity equation here with the acceleration, we've got this rearrangement, which is same dt, except we got 1 and m times the sum of all the forces on a particular particle. And that's actually relatively straightforward. And then with that velocity, we throw that in here, and we've got the position, and we can calculate the new position. So all that's left is to actually work out what the forces are. And that's one of the main distinguishing factors between a particle code or an FEA code or a fluids code or whatever. What type of forces are applied. In a particle code, the forces might be gravity, and it might be two particles coming into contact with one another, and you can calculate the force by knowing where this one is, knowing where this one is, and if you say they're elastic, how much they're overlapping, and you just put a spring, an equivalent spring for that overlap. So if they've overlapped by 1 millimetre, then you imagine that they've compressed by 1 millimetre, and you apply that amount of force. And so you just track where your particles are and do a search between particles at every time step, and any that are overlapping, you put a force between them, and that actually then repels them from one another. You just need small enough time steps that you don't get particles overlapping by a lot, because then you get a very large force. So you want very small overlap, and you control that with the time step, but otherwise it's fairly straightforward to calculate. And in terms of that code I showed you before, that's basically what the students are doing. So particle overlap, and the same thing with boundaries. If a particle overlaps with a boundary, it just calculates a force based on a spring relationship. Now for the more complicated stuff, you'll have friction, and you'll have cohesion, and you can potentially have any number of other things like drag and all of that kind of physics that you would then calculate additional forces for on each one of those particles, and that all gets calculated there every time step. Okay, so there's complicated ways of doing this, but from a very fundamental standpoint, if you're just talking about two pool balls bouncing against each other, then you can effectively have just that little bit of overlap, calculate what the force is based on a spring stiffness relationship, put that force in here, and you can calculate an update in velocity, and then the update in position where they go. So that's the maths behind one of these codes. Now, how useful that is in a classroom depends on how advanced you want to get along that direction. You could potentially get your students to code up or to actually use an Excel spreadsheet, say, to have two pool balls bouncing off one another and just get them to test it at a number of different time steps or something like that. Now that's up to you guys obviously to decide whether that's something that's useful to tie these things in together or whether that's a bit advanced for the students. But what it does is put into context at the very least all of these different theories that they're learning in a very applied sense, a very practical sense. Does that make sense? Are there any questions on that? No? Good. Alright, so that's the main bit of maths for this first part of the presentation. How I'm going to tie it all together is that obviously you've seen what you can have for particles, and I was saying you've got drag and potentially friction, cohesion, all of that kind of stuff. When you have solids, you've got pretty similar equations in the background there, but the main thing that you actually have in terms of what forces can be on that solid is you've got external forces at certain points. So you might have, say, a pressure over here on the left-hand side of this square. And then the internal forces are things like the strength of the material. So imagine springs for each one of those little elements there in every direction, and then potentially gravity and other things. So that's where those forces come from. And another thing that we actually use when you're talking about a stiffness equation in 2D, F equals K delta, so spring stiffness times how much the spring stretches. When you've got one of these solids, we actually have similar spring stiffness equations, but in 3 dimensions, and that's where matrices come into it. And we use a lot of matrices, in particularly these solid ones, where we have force in 3 dimensions and a matrix multiplied by a vector of those displacements in the 3 dimensions. And it gets a lot more complicated than that, but that's a very simple illustration of where matrices actually get used in exactly the same circumstance. All right. And then fluids, we have lots of different forces. So external force, gravity, body force, pressure and viscosity are the major ones with the fluid codes. But similar sort of time steppings and similar sort of strategy for how you actually work out where the fluids are going. You just calculate where their new position is or what the velocity of the fluid is based on pressure and viscosity rather than balls bouncing off one another. And that's basically the three types of, the main 3 categories that a mechanical engineer will use in terms of these types of codes. Alright, why is it useful? Well, I talked a bit about particles. This picture here is a tippler. Has anyone seen a tippler before? So that's an entire rail carriage full of coal. And a big problem that they have with rail carriages full of coal and other bulk materials is a lot of them are designed to have trapdoors. And they open the trapdoor and all the material is supposed to come flowing out. But the same way that if you had a Coke bottle full of wet sand rather than dry sand and turn it upside down, it all gets stuck. So that's called, cohesive or mechanical arching, depending on what the circumstance is. You find that they have a lot of coal getting stuck in these things when they try to use that type of technique. And a lot of the unloading stations that use those will have these massive big jackhammers that come and shake the bejesus out of the actual carriage to try and get the stuff out. This is an alternative, is a tippler, where you take the entire carriage and turn the thing upside down and then back again. You'll see those in most of the sugar mills. They have that kind of technique to get the cane out of the sugar bins. And a lot of the ports have this as well. So you need to work out where the mass is going, what the mass distribution from all of those particles moving up to the edge of that carriage is. Is it going to actually wear the carriage out at the top lips of that? Is it going to break the carriage? What sort of tippler design do you need? All of that type of stuff is really critical. Conveyor belts, hoppers, all sorts of things like I was saying before. Solids, we've got everything from cars to engine blocks to gears to basically every bit of machinery or equipment in a plant or a mine or a boat or a plane or a building. Anything that moves, all of those solids need that exact analysis done on them. And fluids, obviously, we have everything from pipes and pumps to aerodynamics and cars and all sorts of things like that. And mechanical engineers work with all of these things, do a lot of pipe design, do a lot of actual structure design. And some of the examples where, particularly flow simulation. So I was saying that what I was doing over in the States is flow simulation, and so I'll put that into some context in some of the bigger applications of that. This is what I was doing at MIT. So the oil companies want to get as much oil out of the ground as they can. I'll talk about this in a second, but we do a bit of 3D printing. This is reservoir rock. This is dolomite reservoir rock, and the dimensions of this is blown up. This is basically 0.5 millimetre by 0.5 millimetre by 1/4 millimetre. So that's the same as the micro CT segmentation. So what we can do is get reservoir rock and take CTs of it. If you look at that, and then imagine that shrunk right down, you can see how difficult it would be to get a really viscous fluid out of that, particularly when it's combined with gases and waters and things like that. It's that type of rock, sometimes bigger, sometimes smaller, across many kilometres. That is what an oil reservoir actually is. Right, so it's not a big hole in the ground that you just pump it out of. It's stuff that's stuck in either sand or rock that's more horrible than that. And so once you spend 30 years on a reservoir trying to pump steam and chemicals and frack and water behind it and all sorts of things, and you've got hundreds of wells all over the place, you probably leave half of the oil in the ground, and that's a really good result. So you can imagine that with the amount of oil that's being used and how we're basically reaching peak oil and at a point where oil is going to get more and more expensive, getting more than half out of the ground is a really huge thing if they can arrange it. And so what they need to do is characterise what that actual rock sample is in terms of how easily fluids flow in it, what permeability, relative permeability, things like that are. And normally what they do is take core samples and do experiments on it, flush water through it, flush oil through it, and see what those values are. Now, core samples are very, very expensive, and you can only get very few compared to a very, very large reservoir. So of the order of 10, 20, maybe 100 in a really huge reservoir. That's only 100 data points across many, many kilometres, which is very, very coarse. And so the idea is that if we could, instead of doing core samples, take CTs, and we can get CTs of not perfect cylindrical samples. You can get little rock spoil and chips and things like that of rock and do CTs of them. We have a potential to get a lot more data points if we can calculate the permeability on those bits of rock. And so the idea is that you take that CT, you turn it into a digital rock, and then you run this flow simulation on it. And you can get the same things from a flow simulation as you can get from an experiment. The advantage is, as I said, that we can potentially get a lot more bits of rock to actually test on. So as you're drilling, you could actually take that drill spoil and get samples taken and get it characterised all the way along the well or whatever. And so then that information is put into a much larger scale, field scale model where they have all of that data and they work out where to put wells and where to put pumping, water injection wells and all sorts of things. Manage the recovery over the 20 or 30 year lifespan of the reservoir and get oil. That's the idea. And one thing that we're in the process of at the moment is the idea that maybe to supplement this we could do something in a 3D printing fluid test as well. So that's an idealised porous media, and that's obviously the dolomite rock itself. And if we can run the same sort of permeability experiments on a 3D printed sample that we can on an actual rock, then we can sort of have a half measure between the simulation and the actual physical stuff.
You said that you don't do core samples because core samples are too expensive to drill and take. So you just take normal bore holes or drill holes.
Yeah.
You still get your coarse data because you wouldn't be.
So the core samples, you can only get a few of them. And at the moment, this whole digital rock idea is in the sort of verification stage. Across the world, there's many, many groups working on this. So they're working with core samples because we can do experiments on it.
Yeah.
But when you actually drill one of these wells, I don't know how much about drill technology you know, but they're incredibly sophisticated on the actual drill head. So it's not just down, they can go sideways and snake around and direct it. They also have a lot of sensor technology on that actual drill head. So they've got all sorts of stuff that's telling them what rock they're drilling through and helps them direct through the oil. The holy grail of this is the idea that might actually have some sort of a CT-esque ability in the very distant future where you can actually read this sort of information real time as you're drilling through it, work out where the point permeability is. But as that drills through, that drill spoil that gets taken back up, you could actually take the bits of sample and do CT of that in a much sort of longer time frame way of doing it.
And so now you're not just getting it from one sample, you're getting it across wherever it drills to.
Exactly. That's the idea. Yeah. Where before you would have maybe a couple of hits and then you just drill through it hoping for the best. Now you can have a much higher resolution information as you go along. That's the idea, and that's what the oil companies are really really interested in. Because when you've got many kilometres, so the biggest oil reservoir in the world is Saudi Arabia, and it's tens of kilometres across. And when you've got a simulation of one of those field scale models, they run that with close to 1 billion degrees of freedom in the elements on the supercomputers that they have. Saudi Aramco is the company that manages that work. And one of those elements is the size of this whole building combined. So not this room, this whole building is one of those elements, and they've got 1 billion of those. All right, so you can imagine that when you've got that type of rock on a 1/4 mil by 1/4 mil, and it's different between there and the one just beside it, and it's different between there and the one just beside it. So when you've got a couple of hundred data points on something that vast, it's really coarse, and the ability to get more information, even just a little bit more, will really increase your ability to get as much of this out of the ground as possible. So there's a lot of work being done at the moment, and that's what I was working on in the States, and we continue to do a bit of this simulation work as well.
So I missed the point of the regular.
So the ideal one, obviously you can't do anything, engineering, one of the most important things about engineering is start simple and coarse and work fine. So the ideal one is because we have analytical expressions for exactly what the permeability should be in that. So if we can do that in an experiment and prove that next to the analytical ones, and we do that in the experiment and prove that next to the numerical, then we can actually have much more confidence in the real rock version. We do all of the exact same techniques when we're verifying our numerical codes. One of the major reasons we're doing that is because core sample is that big, and that's what you get the permeability on. But we don't have the computer power to do that whole core sample, so we do very small sampling when we do the numerical stuff. But it's unclear as to whether the small sampling on the numerical is not comparing to the core sample because of the scale difference and because you're only taking one sample, or because the numerical isn't accurate. And so we don't have anything to compare the numerical to actually get accuracy. And we get pretty close, but the engineer in me wants something a little bit more detailed. And so by actually doing experiments on the exact bits of rock that we're doing the numerical on, that gives us much more confidence in the numerical. It also gives us potentially another tool to add to the way that we calculate these things. So there's a few things going on there. All right. So, and this is the simulator. So the simulator that I use for that is a smooth particle hydrodynamics simulator, which is kind of like the particles that I was talking about a minute ago, except that the particles behave like fluid rather than solids. So they have all of the pressure and viscosity and things interacting, but it's exactly the same type of code. That's a droplet of water splashing on a surface. And you can see that for the types of properties we were giving it, that was fairly realistic. This is oil and water and a surface, and obviously oil wants to rush to the surface of the water. This is something called the Rayleigh-Taylor instability, which is a very common profile in terms of how the two fluids interact. And the advantage of using the particle method that we do is that it takes into consideration all of those little interfaces kind of naturally, whereas a lot of the other codes that you might use, you have to put a parametric surface around those and calculate where that moves, and it's very costly. So that's another little simulation that we can run with the particle codes. And the idea is that when you're actually in the rock, you've got oil and water and all of that kind of stuff all interacting together. And so if we can get the oil and the water to behave correctly and verify that, then we're confident that it'll work well in the rock. So that's a little bit of the one area where we can use simulation in research and sort of on the cutting edge of things. This is another one. So as you can see there, that's the abdominal aorta that basically goes down from your heart and splits off to your legs. And getting aneurysms in that particular part of your artery is fairly common, particularly in older patients and diabetic patients certainly. And so when you get an aneurysm there, the aneurysm itself isn't necessarily that dangerous to you if it just stays the way it is. The reason an aneurysm is really dangerous is because the wall of the artery is really weakened, and so it can rupture. And once it ruptures, basically you're voiding your heart into your body cavity, and that's the end of you in a very short period of time. So when they find these things, the surgeons need to work out whether to operate or not. And you'd think, well, you always operate, but when you think about how invasive that surgery is, and that a lot of the patients that have these are quite elderly, so 80, 85, 90-year-old person, what is the likelihood that their aneurysm will rupture next to the likelihood that they won't make it to a surgery? And so that's what the surgeon has to weigh up. And at the moment, the way that they do that is, this one's big, we operate, this one's not, we don't. And so what we as engineers want to do is add tools to that step of clinically analysing this, because as engineers we understand how wall stress works, and that solid modelling program that I was talking about, where you've got gears and engine blocks and cars crashing into things, the same sort of techniques to tell you when that's going to fail should work on this and tell us when those are going to fail based on a patient-specific geometry. And so, as I said, we do some 3D printing. One of the major things that are difficult is to take the CT and then turn that into solid computer geometry that we can run simulations on. And so we've got past that, and just for illustration purposes, I've 3D printed one of them. And you can see that that's 1:1 scale of the artery that goes like that, and that's quite a large aneurysm. And so most of the wall tissue that is there is basically stretched over that, and then it has some diseased tissue that's very rigid on the inside there, and then you've got the standard blood flow going on as well. So you can imagine that there's a lot of different things going on there that can cause this to potentially rupture. Pass that around, you've also, in that artery, you've also got muscle response. So the artery pinches down behind the blood, and that's something that no one's ever simulated before either. And so what we're trying to do is come up with simulation tools that actually allow us to model that. And you've got the blood flow, so that's fluid flow, and then you've got the artery, which is the FEA, the solid modelling, and that all needs to interact with each other as well. So that's another area where we're looking. And the reason is that if we can actually work out a predictive, what are the likelihood that that is going to rupture or that isn't going to rupture, then no longer is it just big ones operate, small ones don't, because they find that sometimes the small ones rupture and sometimes the big ones don't. And so it's not just the size that dictates whether these things break or not. And this is just a couple of simulations. These ones aren't ours, these are just from YouTube. It gives you the idea that this is the blood flow, and this is the stress on one of those aneurysms. So you get the contour plot where red is high stress and blue is low stress, and it changes with the beating of the heart, the different blood flow. And so it's a very, very complicated process, much more complicated than any actual standard mechanical engineering stuff, which is why it's really interesting to us. But again, it's very, very similar fundamental theory, just taken to a much more I suppose, detailed end when you've got all of those different moving parts going on. This is another area where a lot of my students actually work. So I supervise the motorsports team, and so we have, we're building a car. We took it to competition last year. We're taking it to competition again this year. There's a competition in Melbourne every year for 20 to 30 universities. And so when we're talking about the fluid flow stuff that I've been talking about, you've got a lot of different areas, but particularly the air intake and also the exhaust manifold to actually optimise. These cars have a 20 mil restriction on the air intake. So I suppose when we actually have combustion in an engine, you need three things. You need spark, you need fuel, you need air. And when you put your foot down on the accelerator, the only thing you're doing is just opening up a valve that allows more air into the engine. And the more air that goes into the engine, the more it burns and the more power you get. Okay? So when you actually put a restriction, and on these cars there's a 20 mil restriction on that intake, so you've got a hole of 20 mil that 4 cylinders worth of air has to go through, you've got to optimise a lot of the air flow in that intake. And so that's what these students are actually doing with simulation and experimentation and all sorts of things. And this is one of the things that some thesis students did. So you can put an engine on a dyno, which basically reads the torque and the power. You change things in the engine and you're going to get different power out. And ideally we want the most power out of our engine that we can. And so what they did, the plenum, which is the sort of the air comes in here and then it goes out 4 runners into the 4 cylinders of our 4-cylinder engine. That plenum is where air kind of collects before it gets sucked into the piston, basically. And the size of that dictates a lot to the different ways that the power of the engine will work. And so what they did is come up with an experimental one where they had inserts where they could change the volume. Then they compared those exact geometries and the dyno testing to the fluid flow simulation and working out that the flow paths were actually nice and smooth and how the air was all moving into the engine, and they could work out a lot about what the geometry should be to optimise that performance. So in a very practical engineering sense, this is where we can use those type of simulation techniques to add to experimentation to actually tell us how to improve a particular machine. Right, so hopefully that gives you a little bit of context where the simulation stuff is getting used. Numerical simulation in engineering is huge, and particularly mechanical engineering. We use it as one of our key tools. The solutions that we do have to be verified by hand calculations and standards and any number of other things, so we don't just rely on this. This is one of the major tools that we use in almost every design that we do. So simulation is very important, and you can see that, as I said, a lot of the fundamental maths and physics that you learn at the high school level is what we're applying here. It's just applied at a sort of a larger, more complex scale. And that's an image that I normally show to school kids, basically just the different streams in mechanical engineering. Thermofluids, design, management, and a little bit of understanding of materials, and some dynamics in terms of springs and that kind of stuff, but I won't go into too much detail because that's not really what we've been talking about today. Right, any questions on that before I move on? I've got some notes for the next part that I'm just going to do on the board because it's equations and calculations, and there's a lot of potential for things like classroom experiments on that. So any questions on that first part before I move on?
Really brief one. What kind of code do you use?
I use C#. So as a programming language, you know Java?
Yeah.
So C# is Windows version of Java. It's like a managed C++, and so the C family started with C, which is kind of similar to Fortran, went to a couple of versions of that, and then C++, which is very similar to C#, except C# is managed memory. So it sort of cleans up a lot of that extra stuff you normally have to deal with C++. So it's a high-level language, and the reason that we use it, and the whole purpose of me going over to MIT was to start this project, which was rewriting these codes into, or rewriting new code, writing new codes into managed high-level languages. Because basically all of the simulation programs that you would buy and spend a heap of money on are all written in Fortran, really old stuff. So when you need to change something, it's an epic sort of job to find the hundreds of different places that things are in, whereas when you have high-level languages like that, it's much easier to update and manage.
Is this what the kids use as well?
Yeah, that's what the students write those particle codes in. Yeah, I get them to use that because that's what I use.
Yes, what's in MATLAB?
Sorry?
What's in MATLAB?
So MATLAB they learn in first year, and I don't really use MATLAB as a code very often. Some people around here do. I tend to prefer things like C# because it's a managed code. But the other thing is C# is free, whereas you have to actually pay for MATLAB, which is a bit of a challenge. So you can use MATLAB for these type of things, but for the large scale stuff where you're actually striving towards a code where you can actually sell to people, MATLAB's a bit of a challenge for that kind of stuff.
So is it worth, I have no idea what C# is, but is it worth kids doing coding beforehand?
They absolutely don't have to, but my opinion of where engineering in general is going is that 15, 20 years ago you graduate as an engineer and you work in a company where you buy the software and you just use it. Now most of the big companies are writing their own, because when you buy the software it's $20,000 to $30,000 per license, so per seat for consultancy versions of it. So you're saving yourself all that money and giving you extra flexibility by writing your own stuff. So I'm a very strong advocate of the better a programmer they are as a mechanical engineer or any other, the more useful they're going to be in industry, because in the next 10 years, we use this much computers now, we're going to be using that much computers then. So the more flexible they are, the better job security I guess they have going forward. But from do they need it to be successful at university in its current form? No. we do programming in first year, and we expect that most of them have no programming background. It's just really easy if they do. Any other questions? Cool. All right. You want to take just a couple of minute break, and I'll just see how the guys are going setting up the gear, and then we've got some notes, and then we'll move on with that. Okay. There we go.